All right, so today is horizontal and vertical stretches to start. Dilation is on the next page. So if you've ever taken a piece of clip art and you have stretched it not proportionally, it gets wide or it gets tall, right? Kind of like a funhouse mirror does. Agreed? So that does occur when, and you did this with parabolas, and I believe we actually talked about that, how your parabolas can get shifted, but they also could get wide or they could get narrow. And that was how we did stretching this way and that way with parabolas. So we're going to be doing the same thing here, and we're going to focus on using coordinate pair rules. And so we're basically are just focusing on writing down the points and seeing what happens when we apply a rule. So if I take this shape ABC, we're going to go ahead and just write down the 3 points. And we're going to do it sideways to make it a little bit easier. So A is located at 1, 1, and B is located at 4, 1, and C is located at, looks like 4, 5. Okay. If we take the rule, take the X and Y pairs, and take the X and multiply it by 2, but leave the Y alone, let's see what we get. So that means every X is going to get multiplied by 2. But you could either say, I'm going to take the Y and multiply it by 1, or you could just say it's just going to move down the way it is. Okay. So let's see what our new coordinate pairs are. So A prime is going to be 2, 1. And B prime is going to be, 4 times 2 is 8, 1, because the Y doesn't change. And then C prime is going to be located at 8, 5. Okay, so all I did was apply the rule to the coordinate pairs. Take a few moments, plot those 3 points, draw, and label your triangle. Please close the Chromebook. Did our triangle get any taller? No, did it get stretched this way? So that's a horizontal stretch. And that's because the X variable had a coefficient, right? So it was K times X. There was some coefficient there. If we had had a number like 0.5, our triangle wouldn't have necessarily stretched wide. It would have gotten narrow, right? Would have become thin. All right, so let's do the same exact process, but this time we're going to change the rule to X, 2Y. So once again, just start out by writing down your coordinate pairs for A, B, and C. It's the exact same triangle. Bless you. And then the A, and so I could even put times 1, times 2 if I didn't want to, if I wanted to talk about multiplying always. The K value is 1, or the coefficient on the first one is 1. Or you could just say I just need to multiply the second one and bring the other one down. And then 5 times 2 is 10. Whoa. When you have your 3 points, you're going to plot them. And connect. All right. It's a pretty stretchy, tall triangle, isn't it? Okay, so that's our vertical stretch. And that's because the Y is being affected by some sort of a factor. Okay. So now we can also start to look at sides and angles. Some angles are staying the same, like a right angle is staying the same, but can you guys tell that angle C got smaller as it got pulled up? Yeah. So clearly these shapes are not congruent to each other, nor are they similar to each other. They're distorted. That's like when a picture of clip art gets stretched inappropriately, right? You could tell when it doesn't look right. You guys all have very, very strong visual perception. So when I use a rule like 2x, 3y, well, I know my shape is going to get bigger, right? But is my shape going to still look like its original shape? Will it still have the same proportions, really? Or is it going to look more stretched? Or, is it getting stretched more? Is it in this direction, or is it getting stretched more in this direction? Yeah, so both are getting stretched, but this is more stretch vertically than horizontal. And it's just going to look, yes, it'll still be a triangle, but it's not like it's the same triangle that was just enlarged for the sake of enlargement. It's not like we used a Xerox copier on it. So not only are these stretches not rigid motions, right? Are stretched rigid motions? Oh, no. Corresponding sides and angles, bless you, are not congruent. But we also don't have that beautiful idea of something that's made in a scaled, idea. So when we look at scaled models of trains or buildings, right? Like when we're looking at Legos, they scale them down so they still look like the real thing, right? Just the mini version. Okay. Or sometimes, you look at architecture plans and then the real thing is blown up. So when those coefficients are different, the image is not proportional to the pre-image. The angle measures can change, and we saw that with the angles that we saw that with the angles that were not the right angle. Sometimes right angles are interesting because of the idea of left and right. Okay, so now we're going to turn the page and we're going to look at when those coefficients are the same. Okay, so when you're ready, go ahead and turn the page. Got it? Okay. Okay, so dilation. So dilation occurs when both the horizontal and vertical stretch is the same. That's when we have dilation. So for dilation, there's a couple things. Our shapes can be enlarged or reduced. So we have shape enlargement. And that's when the scale factor is greater than, so I'm using a greater than symbol, okay, an algebraic symbol, greater than 1. You're going to have shape reduction. When the scale factor is between 0 and 1, so we say 0 is less than k is less than 1. And then the weird thing is if the scale factor does equal 1, the shapes are congruent. And so we don't call dilation a rigid motion overall because we talk about things being in proportion instead. All right, so the details are that scale factor. So the first detail is scale factor. The letter K is kind of dedicated to that scale factor. And the formula for finding it is taking the length of an image side and dividing it by the length of a pre-image side. The other thing that you need is a center of dilation. Which sometimes can be the origin, but can also be other places. If the center is the origin, then the rule is nice and easy. You take your x comma y and you multiply it by the k has to be the same on the x and the same on the y. So you couldn't have two different numbers, but something like 2x, 2y is okay, right? When those coefficients are the same, that's a good rule. All right, so let's just do some examination of these ones up here before we move on. And maybe we won't move on. We'll just kind of figure that out. Okay, so for this one up here, the center is the origin. And looking at our three side lengths, they're all skewed. There's nothing horizontal or vertical that's easy for us to measure. But what's nice about that is we can figure out the scale factor by looking at two corresponding points. So for example, if I look at point D and D prime, and I find their locations, okay? So it's a little bit hard to see underneath, but I can see that D prime is at 0, 8. And if you can kind of look at the grid lines, this is 0, 4. So what do we do to the number 4 to get to the number 8? We multiply by 2, right? So our scale factor is 2. You can see that parallelism, right, is maintained. So if I look at DE is going to be parallel to D prime E prime. Parallelism is maintained. Angles are still congruent. Okay. Corresponding angles are still congruent, but we have to say something different for the sides. So let's go down to this second one so we can figure that out. Okay. So if we look at side AB and side A prime, B prime, okay, so AB looks like it's 1, 2, 3, 4, 5, 6, 7 units long, right? Yeah, 7. A prime goes from -4 to +10. So I'm not counting blocks. I'm using the grid to make my life easier. If I go from -4 to 0, that's 4, and 0 to 10, that's 10, which means the total length is 14. So then if I use this formula where K is equal to image over pre-image, I can now see that once again, 14 divided by 7, this scale factor is 2. The problem with this one is that the center is down at the bottom, so we can't use coordinate pairs to determine the rule. Another thing that's kind of cool about dilations is we can take a straight line, and I'm going to do light green, and I'm going to change it to dotted and see if this comes out okay. And if I start at the center and go to B and go to B prime, right, I can see that explosion happening, moving out from the center. Same thing, A to A to A prime. And I can continue that. I mean, like, that's how dilation works. These lines that go from the center to the pre-image point, the image point has to be on the same line. Okay, so we have this idea of explosion that's going to help us understand where things are. All right, and then when you're done with that, let's just go back one page to kind of just once again understand this corresponding sides being proportional. I just want to show you one last thing. So we're going to go back to the pictures we had. Okay. So for example, let's just use the idea of this one up here. Okay. So if I were to look at A prime, B prime over AB, I could say, you know, well, A prime, B prime is 6 and AB is 3, right? So that's going to give me a scale factor of 2. But when I do C prime, B prime over CB, I get 4 over 4, right? So just kind of look at the sides I'm comparing, right? Our height didn't change, which means that's a scale factor of 1. So here we can talk about our corresponding sides are not proportional because 2 doesn't equal 1, right? It's different scale factors. And that's why it's not a dilation. So that's a good example for us to use as like a contrast to what occurred. We didn't necessarily answer the question that's off to the side. So if I call this triangle ABC, its image is also ABC going in the same order. So the orientation is preserved. So off to the side, it says, does the orientation of the letters stay the same in dilation? The answer is yes. Okay. Side length is not guaranteed to be preserved. Angles are guaranteed to be preserved. So we'll do more stuff with those properties soon. But let's just practice the process of dilation. And you can't dilate a point because a point has no dimensions, but you can dilate a segment as well as a shape. Yep, so we're on page 14. All right, so down here we're at the bottom. So it says dilate each segment by the given scale factor, and it says about the origin. It could also say the word centered at the origin. Okay, so here we go. If we look at this first one, we have a scale factor of 2. So that means for every coordinate pair we have, we're going to take the x coordinate and multiply it by 2, and we're going to have the y coordinate multiplied by 2. So 2x, 2y. Okay. Now you can do these in your head, or you can do them mathematically down below. So for example, if I take a and write down 2 comma 0 as a, and then I say, hey, I'm going to multiply the x by 2 and the y by 2, so that's multiplication, x's. Then my a prime is going to be located at 4 comma 0. So that's pretty easy to figure out. So I go back to my origin, and I go over 4, and I plot that point, and that's going to be a prime. And then the same thing for b. We're going to multiply both the x and the y by 2. So this is pretty easy to do. If we start off with 2, 2, what is our b prime going to be?
4, 4.
Yeah, that's easy. B prime is 4, 4. So we go over 4, we go up 4, we plot b prime. And then when we connect the 2 points, so a couple things. Parallelism is preserved. Length is not preserved, but we can see that the side length has doubled, right? Because of our scale factor being 2. And of course, since the scale factor is greater than 1, it's going to be an enlargement. So we do the same type of thing here. Our scale factor is 1/2. We know that means it's going to be a reduction. We're getting smaller, but something else is going to happen. I'm wondering if you kind of noticed that in the first one, do you see how our segment moved farther away from the origin, right? So when we do a reduction, it's going to get pulled in towards the origin, okay? So we can start by going like this, just, whoops, whoa. Let's see, A is located at 2 comma 4, but now we're going to take half of each one, so multiply by 1/2. And so A prime is going to be located at, so half of 2 is 1, half of 4 is 2. And so we plot the point 1 comma 2. Nope, I just plotted the wrong point. There we go. A prime. Okay, and then we have B, which is located at 6 comma 2. And then you could just say in your head, what's half of 6?
3.
3. What's half of 2?
1.
1. Okay, right? And so 3 comma 1 over 3 up 1 is B prime. And then we can connect those 2 lines, or 2 points to make a line, my bad, segment. And there we go. Our segments are parallel. That parallelism is preserved. Yay. All right, so a line is a one-dimensional thing. You can only go back and forward. So when we do shapes, that's when we see area, right, changing and perimeter changing. When you're ready, you can turn the page. Beep. We also can move the center of dilation. So here it says dilate the segment PQ by a scale factor of 1/2 centered at the point 4, -1. And there's two different ways to do this. So first thing we want to do is go over 4, down 1. Okay. And that's our center. Okay. All right. So method 1 is going to be using the idea of slope. Okay. So for example, if I go from P to the center, it's down 1 over 4. Do you guys agree with that? Yeah. Okay. So the slope is down 1 over 4. If I take both of those and multiply it by half, right? Change in y over change in x. So what's half of 1? Half, right? So down a half and over what's half of 4? 2, right? So I know that looks weird because it's a complex fraction, but if I go back here and go down half and over 2, I'm like right on the middle of that number 2. Can you guys tell that that's going to be P prime? In fact, I can take like a straight edge and line it up so like the 3 points are all in the same line, right? Do you remember that idea? In fact, I could be crazy, so crazy that if I wanted to, I'm going to do this with yellow. Do you see how I can go down half over 2, down half over 2, right? So this is like a weird scale. So we can use slope and take those slope triangles and divide them in 2, right? By 2, so we get half of that. So that's one way to do it. The other way to do it is that you would do the same thing we did for rotation, and you would move the axes. So you would put your axis through the center and recount your points. So we'll make a class decision about what we want to do. Does that make sense? All right. So remember, when we moved the axes, we went like this. Maybe I'll do it with a highlighter. We said, hey, I want my axes to now be through here. Remember that? And then what we said is, well, P is not located, or Q is not located at 6, 3, right? Q is located at, I need a real color here. Q is located at, from the center, over 2, over 2 and up 1, 2, 3, 4. Over 2 and up 4. So then if I were to multiply each of those by half, right, this is what we did before. We did the rule, right? We would get Q prime is located at 1, 2, which if I go back here, I'd go over 1, up 2, and plot Q prime right there. And once again, Q prime is still located on the same like blow-up line we had before, right? So either way, these points are going to line up again, right? They all have to be on that same line going back to the center. And if I connect the 2 points, P prime and Q prime, I get my segment, which is half as long. Let me just get out of my own way there. Half as long in parallel. Do you guys have a preference what you want to do? Do you want to move the center like we did for rotation, or do you like the slope idea?
I like move center.
Move the center?
Yeah.
Okay.
So
all right.
Wait, question.
Yes.
So if we move the center, what
would happen for point P?
Yeah.
Okay, so if we move to the center, point P then is located at back 4, up 1, right? Back 4, ooh, ha, ha, ha. Let's fix that. Back 4, up 1. So we would still take half of it, right? Half, multiply by half, multiply by half. My pen is really sloppy today. And we would get back 2, up 1/2. And so you can kind of see it, right? Back 2, up 1/2. Okay. So both methods work. Honestly, sometimes I'm like, I'm just going to draw those blow-up lines where they're supposed to be, and then I know my points have to be on the blow-up lines. And I think that's a good strategy to make sure like you're going in the right place. All right, so let's practice a couple more, and then I think you have practice. You definitely have a practice page. I don't know how much more practice we have here in the book. We'll find out. All right, so it says dilate triangle ABC by a scale factor of 2, centered at the origin. So there it is. All right, we're at the origin. All we have to do then is write down our 3 points, A, B, C, because we're using the origin. Okay, so A is located at 1, 1. We've used this triangle many times. 1, 1. B is located at
4, 1.
yeah, and C is located at
4, 5.
yeah, 4, 5. Now for every single one of these, and this actually was the triangle on the previous page, on the stretchy page. So now, since we're doing a scale factor, we're using 2x, 2y, right? We're going to blow it up in both directions, both horizontal and vertical. So all you're going to do is go times 2 times 2, and you're going to do that all the way across. It's up to you if you need to write the times 2 times 2 underneath every single one of them, right? So we have 2, 2 for A prime. For B prime, we have times 2 times 2. Right? So we're going to have 8, 2. And for C prime, we're going to have times 2 times 2. Oops. We're going to have 8, 10. So let's blow our triangle up. Plot our new points. And then use your straight edge to connect your points. Yeah, the dilation just overall. I mean, dilation is nice. It's just one.
Yeah.
I mean, counting is not difficult. So probably the rotation is not easy to perform. It's okay. All right, did you get something that looks like that? Yeah, cool. All right, so you can see that the angle measures haven't changed, right? Corresponding angles are going to be congruent. Corresponding sides are proportional. So now let's do this again, but now we're going to move our center. So let's see how that changes things. So we made a decision up there. So we're going to, well, I don't know why I keep forgetting to change. We're going to take the center and draw the axes through it. Draw new axes. So 0, 3 is up here. Okay. And then you probably want to take either a thin highlighter or a thin colored pencil or something like that and draw your axes through it like that. So now we got things in different quadrants, but that's going to be okay. We're just going to follow the rules that are there. If we're doing a scale factor of 2, we're going to go x comma y becomes 2x, 2y. We're going to write down our 3 original points, but based on the new set of axes. So A is not going to be positive 1, 1. It's going to be positive 1, but then it's going to be down 2. Does everybody understand that? Yep. So A is over 1, down 2. So B is going to be over 4, down 2, right? So from the origin, which is now our center, which is now our origin, right? Over 4, down 2. What's C going to be? Over 4, up 2. Okay, so now we're going to go ahead and multiply every single number by 2, which is our scale factor. Yes.
I'm confused.
Talk to me.
Oh, wait, never mind.
Okay. Do we know why it's a negative 4? Somebody say something about the negative 4?
No, it's okay. I got it.
Are you sure?
Yeah.
So it's based on the fact that this is now 0, 0, right? Okay. And if you don't like that, I can show you the other method. Okay. So I go here and I'm going to plot A prime. I'm going to go over 2 and down 4. So 1, 2, 3, 4. Here is A prime. A good way to check if I'm on the right track is to simply draw that line. Are all 3 things aligned, right? So I know I'm on the right track if all 3 points lie on the same line. Okay. I go back here. B is located at over 8. 1, 2, 3, 4, 5, 6, 7, 8, and down 4. Here is B prime. And then I can also go back still and check, are all 3 points on the same line? They are. And then my last point is over 8 and then up 4. So I'm up 4 from here. 1, 2, 3, 4. And there's C prime. So my triangle now looks like that. But it's not like it's a different triangle. It's still the same size as the one up above, right? It just got shifted to a different space because of where the center is. Does everybody agree with that? Like it's still a 6, 8. It's a 6, 8, 10 triangle. They're both the same size. They have the same exact area. They're just in different places because the center moved from here, right, at the origin, to somewhere else. But that whole idea of the points lining up still works. Okay. All right, how are we doing? Okay? All right, turn the page. I think we got 2 more things to think about, and then we're done. Is this all one page? It pretty much is one page. Okay, so here we are. So sometimes instead of being asked to dilate, they ask you to find the center of dilation, or they ask you to find the scale factor. So for center of dilation, it's using those blow-up lines I was just talking about. You draw lines through each pair of corresponding points. So like, for example, through A and A prime. That's a set of corresponding points. And that will take you to where the center is. Hopefully you can kind of tell if the shape is getting bigger or smaller based on looking at what's on the grid. If we want to find a scale factor, typically it's easiest to compare the lengths of two corresponding sides. So we're going to go ahead and think about the scale factor being the image over the pre-image. And then you should be able to tell that, you know, if it's getting large, the scale factor needs to be greater than 1. If it's shrinking, it's going to be less than 1, between 0 and 1. And then if you can't find a side length easily, then you're going to go to slope triangles or look at those blow-up lines, and it's not hard to tell. It actually is quite easy. Okay, are we ready to try some? Okay, so down here on our first one, you're going to want to take your, let's do all the centers first. That's just the, we're going to use our straight edge over and over again. And if, Adeline, if you want any help, just let me know. Okay. So if we go and look at our straight, take our straight edges and do this, I'm literally going to line up corresponding points. So here's L and here's L prime, and I'm going to draw a line. Now you might be like, well, which direction do I want to go? Do I want to go up this way, or do I want to go down that way? And so that's kind of like where you need to make a decision. Do you think the point is up above or down below? Maybe you don't know yet. But as soon as I go to draw M through M prime, can I tell where the point of intersection is going to be? Yeah, it's going to be somewhere over here. And I'm a little bit sloppy right now, so I'm also going to do the third one to really make sure I do get a proper point of intersection. I think I can tell where it is. I'm going to double check, and you guys are going to check my work as well. I believe it's going to be right here, which according to the, this is the origin way over here, I'm getting over 1 up 5. Is that what you guys got?
Hold on, let me just do this.
All right.
Okay,
So if this is our origin down here, and sometimes it's good to just put a circle around it. So then over 1 up 5, that's the center. So let's keep on finding centers first. Let's practice that.
I got 1,5.
Yep. All right, so now we're just going to draw lines. You want to have, like, check at least 2, but you might need to check a third one to really make sure you've landed on the point. Here we're going to have 4 different lines if we use all 4. What's nice with these is some of them are vertical and some are horizontal. So, for example, here, or D is vertical. So D prime D, and I'll switch colors here to like a pink. D prime D takes me up. Not sure exactly where I'm going yet. So that first line is going to be a bit of a guess. But by the time you get to your second line, you should start to see where things are going to intersect. And it might take a couple tries to really make sure you're all lined up. Oh, here's our vertical or horizontal one. The C's were horizontal. And so you might be able to find the point, but now you got to be like, where in the world am I compared to the origin? So hopefully you got this point right inside of the smaller A, B, C, D, which that makes sense. If something is going like this and the shape is inside the shape, then the center will be inside the smallest shape. When you have things that are moving away from a center, right, it's not necessarily in the shape. So now compared to the, oh, it's way over here. Do you guys see the origin way back there? So now we got to get that point compared to the origin. So we're down here in quadrant 3. Did you get that for your coordinate pair? Awesome. Okay, so now scale factors. So a couple things to do when you're looking at scale factors. You want to look at the two shapes and see like, okay, I started at L, I became L prime. So notice how we're getting pulled back. That means our scale factor has to be between 0 and 1, right? This is a shrinking situation. And right now, I don't have any horizontal or vertical line, so it actually makes it a little bit harder. But can you tell what happened to this length? It got, and how much smaller did it get? Can you tell that it's been cut in half?
Yes.
Yeah, like if you were to go, so this is the idea of slope triangles. If I were to go down to over 10, right? Can you guys tell that this is down 1 over 5, right? So the slope triangle got cut in half, which means my scale factor is half, or 0.5. So that's the thing. If the image is smaller, which this one is, it's got to be a number between 0 and 1. Now in this one, can you guys tell that we're getting bigger? Yeah. And then this is where you might be like, okay, this is a little bit hard. This is like, what do I want to compare? For me, since we have side length AB, which is horizontal, we can count how long it is. So side AB is 3 long. How long is A prime, B prime? Are you guys getting it to be 12 long? Okay, so we know that the scale factor is going to be greater than 1 because this is an enlargement. So we would never subtract those two numbers. We would take the image and divide it by the original. And that means our scale factor is 4. So the side lengths are 4 times longer. The perimeter is 4 times longer. Did the angles change? No, because like if you had a right angle and then multiplied it by 4, that'd be a full circle. That'd be weird, right? You can't do that. So the angles are congruent. All right, so one more question in our note packet, and then we're done for today. It says triangle ABC and triangle ADE are graphed on the set of axes below. Describe a transformation that maps ABC onto ADE. So when you look at a picture, first they're going to be like, hey, are those shapes congruent? Are those two triangles congruent? Congruent means equal size. Is triangle ABC the same size as ADE? No, they're very different sizes. Okay, so there's that. So if the triangle is this different size, then our one and only choice would be dilation, so long as we have a scale factor, right? So we are going to use dilation, and then we need 2 things to describe dilation. We need a scale factor, and we need a center. Okay, so your details. Scale factor and a center. Does anybody have any ideas of what the center might be? Are all the points moving? What point's staying the same? A. A is staying the same. So if it's staying the same, that's going to be the center. So centered at point A. Okay, so the next thing to say to yourself is, self, do I have any horizontal or vertical lines? I do not. So let's look at some slope triangles. If I were to go from A to B, I would go up 4 over 1, right? So up 4 and to the right 1. Well, what's happening when I go from A all the way up to D? We're still going up and to the right. Yeah, we go up 12. And then we go to the right 3. And so now you're just asking yourself, well, what do I do to 4 to get to 12? What do I do to 1?
Multiply by 3.
Yes, multiply by 3. So guess what our scale factor is? 3. Okay. So now we're going to kind of just work on some of that language of it's not a rigid motion, but these two shapes are proportional. So we say they're similar. Okay. So two figures are similar if, and we can write it this way, triangle ADE is similar to, so it's just the squiggle, just the tilde, is similar to triangle ABC because dilation preserves angle size right? So angle A is still the same size as angle A, right? You could say angle CAB is the same as angle EAD, like that. So angle size is preserved and corresponding sides are not congruent, but they are proportional. Corresponding sides are proportional. And sometimes it's helpful to just kind of memorize that definition or statement. And eventually you do get your aha moment during the year because we go back and we do a whole nother unit on similar triangles. Like we are going to play with proportions for a chunk of time. But if you start to get in your head this idea of angle size and that should say sides. Nobody corrected me. Corresponding what? Sides. Sides are proportional. Sorry about that. Corresponding sides are proportional. There we go. My bad. If you can start to glue some of those statements into your head, it makes your life a lot easier as we move forward. Yay! All right, so that's the end of that lesson. How are we feeling about it? Okay, have we all decided that we're going to move the axes to do dilation? Okay, so here we go. We got some practice for you. There's 2 on the